Hey, welcome back, my friends. Today we're talking about mechanics and materials, beam design. We're talking about wide flange beams. What the heck is that? It's just an I-beam, y'all. Don't get all freaked out. It's just an I-beam, okay? We got a little old problem here, okay? There is our load. We're going to try and design that beam to carry that load. What does it need to look like? It needs to be an I-beam. It needs to be a wide flange beam. But which one? There's a bunch of them, okay? So what we're going to need is, we're going to need our, well, I'll tell you what we're going to need. We're going to need our textbook, and we're going to need this. Bam! Appendix B. That's what we're going to need, Appendix B, which is the wide flange beam tables, okay? Now there's one table that's freedom units. That's what we're talking about here. And there's a metric table as well, okay? But today we're talking about freedom units. So I got my table ready to go, okay? Now, there's like 100 beams on there. How do you pick the right one, okay? Well, you need to know something about what we call the section modulus, okay? And the section modulus tells us about the geometric cross-section of the beam that we're going to need. And it goes like this. It takes M max, right? The maximum bending moment on that whole beam, and you divide that by sigma allowable, which handily is given here, okay? So sigma allowable for this beam is 22 KSI, tau allowable 12 KSI. Select the lightest beam with the shortest depth. The depth is the top to the bottom. So if you're talking about like an I-beam here, okay, D is from here to here, okay? That's D. So we want the shortest depth and the lightest, because the way they sell these beams is they sell them by weight, right? So every foot of this beam, depending on how thick it is going to be so many pounds. The heavier it is, the more expensive. The more steel there is, the more expensive it's going to be, okay? So we're going to see how to use this equation. I'm going to show you how to use it. That's called the section modulus. Well, if we need the biggest bending moment, do you know what that means? And also we need to check this guy, right? You know what we need for him? For that guy, we need this guy. So if we're going to find Vmax and Mmax, that sounds like a perfect job for our very favorite thing in the world, shear moment diagram. I love shear moment diagrams, y'all. They're so fun. Let's go. Okay? We're going to do this problem here, and let's see if we can get it. Step one, let's start with, global equilibrium, okay? All right, so we've got over here, an AY, over here, a reaction, BY, and then this, boom, rectangular load right in the middle of that, 10 times 1.2, that's 12 kip-ft. Okay, so let's just find global equilibrium. Let's take the moment at A. And we get 12 rotating as negative, minus 12 times how far away? 4 plus half of 10 is 9, okay? And then we get BY, which is positive, times what? 10, 20, eh? 20, all right. So move that to the other side. 12 times 9, 108. Right, 108 divided by 20. I just did 105. 8 divided by 20 is 5.4. And that's kips. Okay? And remember, up stuff equals the down stuff. So if that's 5.4 and that's 12 down, 12 minus answer equals, boom, this one, 6.6, okay? Beautiful, beautiful, beautiful. Okay, now, let's see if we can draw ourselves a little shear moment diagrammy for your mammy, and we'll find out where the biggest V is and where the biggest S is, okay? Not S, V and M, okay? So here we go. Here's the V diagram, and here's the M diagram. This one's going to be in shear force, kips, and this one's going to be in foot kips, moment down here, okay? So foot kips, okay? And what do we got? We got this. It's where distributed load starts, and it goes to there. And then here's the end of the beam over there, okay? Okie dokie. Let's see. We start here. First thing we hit, AY. Might as well jump, okay? So jump up, boop, to 6.6, okay? And then we go. No change, no change, no change, bam. All right, now what? Well, now we got to go down 12, okay? Which takes us down to 6.6 minus 12. Better be 5.4, okay? And then we go across here, no change, bam. And then guess what? 5.4 at the end, whoop. Take me home to the place I belong on my shear graph, back to 0. Everybody. Okay, fine. This is a plus, this is a plus, this is a minus, this is a minus, right? Which tells me that this graph down here is going to go uphill, uphill, downhill, downhill, okay? Now, one thing, before I get too far along, sure would like to know what that distance right there is. And we can get that pretty easily with similar triangles, and we can do this, right? This distance here was 10, so we can say 10 is to 12 kips as, what, 6.6 kips is to that distance right there, right? X. They're similar triangles, right? We're doing this gigantic triangle to that little triangle. They're similar, aren't they? Okay? So that's move that over there. 66 divided by 12. 66 divided by 12 is 5.5. So this must be 4.5. Okay? Now we can do the graphic method because we don't have a parabolic curve crossing the axis. So right here we got, what, 6.6 times 4. 4 times 6.6 equals 26.4. Okay, put a circle around it because that's an area. This one over here is 6 times 5.4. 6 times 5.4 equals 32.4. Okay, that one right there is 1/2 base times height, right? So 6.6 times 5.5 equals, divided by 2 equals 18.15. Okay. And then this guy right here is 4.5 times 5.4 equals 24.3 divided by 2 equals 12.15. Okay, if you remember we do that, we do these little areas because those areas are how big our moments are going to be down here. Now, if we just look at this real quick, right, question number 1, what is V max? What's the biggest shear force on that beam? Well, is it 5.4? It's 6.6, okay? So 6.6 kips. That's one of the things we need. The other one we need is this guy right here, okay? We're fixing to get it right here. So, step 1, start at 0 because there's no moment. Go uphill 26.4. Whoop, there we are, 26.4. Go uphill some more, 18.15. So, what? 26.4 plus another 18.15 equals 44.55. Okay, so that's going to be right there because our graph goes from positive to negative. So what are we going to have? A humpy-do. That's right. At that point right there because it goes from positive to negative. So we're going to go, burp, we're going to have a little peak-a-roni there, okay? And it's going to be fast, then slow. Whoop, and then slow. Steep, flat. Okay, are we good at these or what, y'all? 44.55. Okay, 44.55. I think that's the number we need up there, right? Because now what? We're at 44.55. We're going to go downhill 12.15 minus 12.15 equals 32.4. Oh, isn't that convenient? And how do we go? Slow, then fast. Okay, that's 32.4. That's a 3. And then what? We got 32.4. Hey, take me back to 0. And there's my graph, okay? So the number out, all of this, which we learned in statics, right, is to get these two numbers, that one and this one, which was, I forgot already, 44.55. And that is foot kips, okay? Boom. We haven't even touched our problem yet, y'all. Okay, but I think we're there, okay? So let's calculate this guy right here, S max, okay? S max is equal to M max, which is this guy, 44.55 foot kips. Uh-oh, that's in footses, and I want them in inches, okay? So a foot is 12 inches, right? Bloop, bloop. Now I'm in inches. Divided by sigma allowable, which is right there. 22 kips per inch squared. Now the inch squared is going to go on top. I already got an inch up here from right there. So it's going to give me S in inches cubed, okay? So we got 44.55 times 12, and then divide that by 22 is 24.3. And that is our S value. Again, this is inches cubed, not a volume, okay? And it represents the geometric properties of our cross section. Okay, so now it's time to get out our book, okay? So what we're going to do is we're going to get our book and we're going to cruise all the way over here till we see a column that says S for bending around the X, because we're bending this way around the X, okay? Bending around the Y would be into the board. We're not doing that, okay? Bending around the X. So what we're going to do is we're going to read down this list and we're going to find everything that's bigger than 24.3. What if there's a 24.29? You can't pick that one. It won't carry that load. It has to be at least 24.3. Can it be 25.6? Yeah, that's no problem. It can be bigger, just can't be smaller. So let's see what we come up with. I'm going to write down all the choices that I find. Now remember, there's 2 old pages of these, okay? So I'm looking for numbers around 24.3. And let's see here. I'm coming up. Okay. Well, the smallest that one goes, that's pretty big still. I got myself a W16 by 26. And that is a 38.4. That's way bigger, isn't it? Okay. Keep going. Okay, here's a 29, a 14 by 22. 29, that's bigger than 24.3. Okay, keep going. There's a 25.4 in a W12 by 22. Okay. It's bigger than 24.3 though, isn't it? Okay. And let's see what else we got here. Ooh, there's another one. W10 by 30. W10 by 30. And that guy was also 32.4. Okay. And then any more? There's a 27.5, a W8 by 31. And that one was, what did I say? 27.5. And one more, maybe a W6 by 15. Nope, I'm on the wrong column. No, that one won't work. That one will not work. Okay, sorry. I was on the wrong column. I thought that was going to be okay. That's way too little. Way too little. Okay, so these from Appendix B are my choices. Okay? What are we supposed to pick? How do we know this? There's two things here. Number one, there's this first number. Okay? That first number is a rough whole number estimate of how tall the beam is. D. It's not exactly, okay? This beam is not exactly 16. It may be like 16.24, okay? But it's in the 16-inch neighborhood, okay? So this one is D for depth. This one is in pounds per foot. So this tells me that that beam, every foot of it that I have weighs 26 pounds. Every foot of that one weighs 22 pounds. 22, 30, 31. Now, what are we looking for? Here we're looking for the lightest, okay? So pretty much all of these beams will do the job, right? All of them will do the job. But too heavy, too heavy, too heavy, okay? Now, these two are tied at 22 pounds per foot, but it also says the shortest depth, okay? So maybe there's like a size constraint on the job where we don't have very much vertical space where this beam's got to go, right? We need the one with the shortest depth. So that would be this one right here because it's got about a 12, okay? Now, we can look that up because in our table also, right, we can go to this guy, 12 by 22. Where is he? He's over here, 12 by 22. And I can look him up and I can go second column over is depth. And it says it's 12.31. So like I say, it's not exactly 12. It's 12.31, okay? But it's in the ballpark. It's still less than 14. What was 14? 14 by 22. He was 13.74. So he's definitely taller, okay? So that's our beam. You are the winner, okay? You are the winner. Now, last thing. Does it meet this criteria? Does it meet that criteria? We better check it, right? Now, if you remember from our last video, shortcuts for I-beams, okay, shortcuts for I-beams says that we can do tau equals V over A, but A is special. A is just this right here, okay? So it's the width of the web times D, the height. Now, we already know the D. It's 12.31. Now, inches. Now, we can look up D also, the thickness there, and it's called T sub W, the thickness of the web, and a 12 by, what did we say, 22, right? 12 by 22, yeah? 12 by 22, the thickness of the web is 0.260. So a little more than a quarter of an inch, okay? 0.260. Okay, so now we need our calculator because we need this area here, which is 12.31 times 0.260. That's 3.2, okay? 3.2. And then we got V. What is V? V is, 6.6. Now this is inches squared. That's kips. So this is KSI, isn't it? So 6.6 divided by 3.2 equals 2.06, okay? So our tau is 2.06 KSI. That's the maximum that we would see because that's what the maximum V is, okay? But it says this beam can handle, the material can handle 12 KSI. We are like wicked underneath that, aren't we? So we're like totally good, man, okay? So we can put a big fat check mark. We checked it. We looked at it. We designed your beam. Go to the store, buy that. So if this is like if you go down to the steel store in your town and you said, give me a W12 by 22, I need 15 feet of it. That's like a part number. They would say, okay, we know right what that is. We'll go get you 15 foot of it, right? So these are like part numbers, and they are international, okay? So these numbers work anywhere you go. So beam design with wide flange beams and how to use your Appendix B. Hope that helped. See you on the next video.